Hello again. In the last video, we found the exact running time for insertion sort, which gave us this absolute doozy. And guess what? That was pretty much useless. Good news though, you likely won't ever have to do that again unless you have a really weird Saturday night. Generally speaking, the extra effort that it takes to get an exact running time on functions like this is really just not worth it. So let's find a better way. Say we have a function that describes an algorithm's exact running time, something like 2x squared plus 2x. Once our inputs become large enough, even as they tend towards infinity, these multiplicative constants in lower order terms become irrelevant because of this highest order term. And if you unrepress your high school memory for a second, you might recognize this as something similar to the concept of a limit. So in our function here, x squared is really what is defining the order of growth for the runtime of our algorithm. It is what is really throwing its weight around. Once we only consider these huge inputs, that they are so big that they make these lower order terms irrelevant, we step into something called asymptotic notation. And a topic that is wrapped up into this asymptotic notation is something called Big O notation, which you might have heard of, and it is what we really care about as programmers. As we go through this, bear with me for a second, it's going to get a little mathy. A part of asymptotic notation is something called Big Theta notation. Let's talk about it. Assume we have some function g of n. Assume also that there is some function f of n that describes the runtime of some glorious algorithm. Now make another bold assumption that there are some constants c1, c2, and n0 such that c of 1 times g of n is less than f of n, which is less than c2 of g of n for n greater than n0. Holy shit, I hope you ate your pretentious educational breakfast. How about we draw a graph so this makes a little bit more sense? The mathematical statement looks like this on a graph. Much easier to read. We are simply looking for a function g of n that when we multiply it by some constants, 2, 3, a billion, whatever, we can create a top and bottom bound for our function f of n. So when we have found a relationship like this between two functions, we can say that f of n belongs to or runs in big theta of g of n. Big theta of g of n is actually a set of functions, and we are seeing if we can place our function f of n into that set. And if we can create a graph like this, then we can safely assume that. Let's remember the function that we used just a minute ago. F of x is equal to 2x squared plus 3x. But remember, in asymptotic notation, we are concerned with the really big inputs in the highest order term. Now our job is to find a function that when we multiply it by some constant c1, we can find an upper bound for our function, and when we find another constant c2 and multiply it by our function again, we can find a lower bound. In this case, x squared fits that bill nicely. We can multiply x squared by 2 to find our upper bound, and we can multiply x squared by 1/2 to find our lower bound. So we can now say that our function f of x is equal to x squared belongs to big theta of x squared. And if you notice, this is really just to give us an idea of the order of growth of our function. How is it going to behave as inputs become very large? We're not looking for an exact running time, but we want an idea of what the running time looks like. And that is big theta notation. So what is big O, and why does everybody care about it? Big O is the exact same thing as big theta. The only difference is we are only concerned with finding a function that is an upper bound for our algorithm. If we can find this, we can say that we've found the worst case running time of our algorithm, because our function f of n is never going to go above the upper bound. And this is why everybody wants to know about it. Think about this in terms of space. If I have an algorithm that in the worst case is going to take n squared space, and another algorithm that only takes worst case n space, then by selecting the algorithm with the better worst case, I can half the amount of storage that I need. So you now understand the theory for big O. And the opposite of big O, we have something called big omega. And big omega is the same thing as big theta, except we are only looking for a lower bound. And if we think about it, this provides the best case scenario for our algorithm, because our algorithm is never going to pass below the lower bound. It is the best case. And in reality, we aren't concerned about the best case most of the time. What we really want is the worst case, big O. And alongside all of these big Greek letter notations, there is small letter notations. There's small theta, small o, and small omega. And these fun size versions are not required to provide a tight bound. With our big theta, big O, and big omega, we're trying to find a function g of n that is as close as possible to our original function f of n. The fun size versions don't have any such restrictions. So if I have a function that describes my running time n, I can provide a little o bound by saying that it runs in little o of n factorial. It does provide an upper bound, but it's not particularly useful. If you would like to learn more about these, I would just skim over CERN Chapter 3, or if you're a masochist, take a look at Knuth. So that's the video. This is the theory behind asymptotic notation. And in the next video, we're actually going to work through some examples of code in order to find what bubble they fit into. So if you liked the video, like and subscribe. If you hated the video, dislike it and leave me a comment. See you in the next one.